Well, welcome everybody again to another IPARCOS astro-seminar. Today it is a pleasure for me to introduce Clayton Strawn, that is a PhD student in the University of California in Santa Cruz, that he's working under the supervision of Professor Joel Primack, and also in collaboration with people working on the CGM studies, like for example, Cameron Hamels and also Jonathan Stern, both in the States. And basically, the Clayton's thesis revolves around that, around the studying the CGM around Milky Way-like galaxies, but well, probably in several a range of different galactic masses. Now focusing first in his first work on a Milky Way size system. And well, basically today, Clayton will talk to us about this project on the CGM and the outskirts of galaxies, and also just to say that in the future, in the very close future, Clayton is going to lead one of the projects within the Agora collaboration that is just studying how the CGM changes on when you use different numerical codes to simulate galaxies. So thank you a lot, Clayton, for accepting to be one of the speakers of these IPARCOS seminars. And when you want, you can start. Thank you.
All right, yeah. Thanks so much, Santi, for that introduction. You left out a key collaborator of mine, which is, of course, you. You'll come up in this talk as well.
Okay.
Yeah, let's go ahead and we'll get started. I'm gonna share my screen. So I should, I click this, click share. You'll see slides, okay?
Yeah,
cool.
Perfect.
All right, so welcome everybody. Good afternoon for you. It's morning here in California, but and today we're going to talk about PI streams and CI interfaces. So how different ionization mechanisms can help us distinguish phases in the CGM. So there's a few acronyms going on here. We'll try and make all those clear, I think, fairly quickly. So the main topic of what I'm going to talk about is about galaxies, and more specifically about this region outside of galaxies called the circumgalactic medium. So the current kind of paradigm of galaxy formation and evolution is that a galaxy, is a collection of stars and gas and dust and other things that is inside of a larger halo of what's called dark matter. So this dark matter halo is significantly more massive than the total amount of stars in the galaxy and extends out significantly further. So they live in the center of this roughly spherical halo, which has a characteristic size within which it's gravitationally bound, and that the radius of that spherical halo is called the virial radius, or RVir. And a galaxy is about 0.1 RVir. So it extends much further out than the galaxy, but it's not just full of dark matter, even though that makes up most of the mass. What also is going on inside the halo, but outside the galaxy, is that there's a lot of regular baryonic matter. So like, ions, atoms, etc. And so that regular matter is really important for kind of two reasons. One is just because it's a lot of the baryonic mass of the universe. We already know that we can't appeal to the universal baryon fraction without noticing that like we don't have enough baryons inside galaxies to actually make up for the cosmological fractions that we need. And the second reason, and so we just want to know about it for that reason, but the second reason is because it also controls what's going on in the galaxies, because this inflowing gas, the CGM is the place that gas has to flow through in order to fuel star formation, because in order to keep forming stars, you need to keep generating additional, you need to keep getting cold inflowing gas. And you have inside the galaxy, you have feedback processes like supernovas going off and AGN and stellar winds and things that are shooting out energy and outflowing gas. So the CGM is where all of that happens. And that is understanding the whole story of galaxy evolution is tied up with understanding what's going on here. So how do you actually study it? And this is kind of the trick, is that it's difficult to study the CGM, because unlike a galaxy, when you look at a galaxy, you can just look at the stars and you can get a sense, okay, well, I can get the colors of the stars, I can get the velocities of the stars, I can get a lot of information from that. But in the CGM, it's really low density, right? So we're looking at this big cloud around this galaxy here, for example, It's really so low density that you won't be able to see too much emission or like emission maps, except for very, very close galaxies. So usually what we look at is absorption spectra. So what that means is we look at a background object, usually a quasar. We say, okay, we know what the spectrum of a quasar is supposed to look like. So when the light gets to us and it's missing certain key wavelengths, we can say, oh, that quasar light must have gone through a cloud that absorbed at those key wavelengths. So, because quantum spectra of ions and atoms is like each ion has sort of a characteristic photons that it can absorb, and most of them will just pass by and not be absorbed. So what we do with that, how do we use this very limited amount of information? Like we get one sightline per galaxy, if that. So the way that we want to get as much information as we can out of these small amounts of data is by using many different particles as tracers. So we have different ions in the CGM that we expect to trace out different gas phases. So this graph here shows kind of how we trace out gas. So this is density on the x-axis and temperature on the y-axis. And so each of these ions here is supposed to trace out gas at roughly that temperature and density, right? So we use like cold ions, so things that are not ionized, like H1 or sodium 1, and then to trace out cold gas. Cool gas is like low ionization states, warm gas is like higher ionization states, hot is very high ionization. By the way the terminology works here is that the ionization state is denoted by a Roman numeral. So oxygen 1 would be non-ionized oxygen, oxygen 2 would be ionized once, all the way up to oxygen 9, which has lost all of its electrons, and now it can't be ionized any further. So what we say is that this is a very sensitive tracer of gas state. So if you see oxygen 6, you can say, oh, I know that that's in a cloud that's like slightly more low density than an oxygen 5 cloud, because each of these points on here is its peak temperature and density. But this can be a little bit misleading, because what if you have gas that's not just along this line, right? This is sort of the peak temperature and density, but you can have gas down here and that'll still have ions in it. This will be, if you see oxygen 6 and it's down here, how can you distinguish it from oxygen 6 that's over here, or oxygen 6, along this line at this point or something? So we have to figure out like what fraction of an element is at a particular state, but not just along, this basic picture, but anywhere in this 2D phase space. And so the complication that we have to deal with is the following. You can get ions from two different mechanisms. First mechanism that you can get ions from is from photoionization. So this is basically when you have an atom that's like just sitting out in space, and it experiences some kind of incoming background radiation. So there's this background radiation just permeating throughout the CGM and throughout space, which is essentially the reason for why we have this epoch of reionization, right? We have the quasars are starting up, supernovas, other kinds of forms of light, and this background radiation just kind of permeates all space. And so the less dense you are, the more photons you get per ion, and so therefore the higher ionization you get, right? So if at very high density, your photons can't really penetrate your cloud, and at very low density, you can get more and more photons that penetrate into the cloud. And the other thing that you can get ions from is from what's called collisional ionization. So this is where ions collide with each other at high speeds and knock off electrons. So this depends on temperature, and it doesn't depend on density really, because even if you're twice as dense and you have twice as many collisions, you also have twice as many electrons to recombine. So it'll end up, being only a function of temperature. And in some ways, it's really just the definition of temperature, right? The definition of temperature is the average kinetic energy of atoms, and therefore the average number of collisions and the average kind of amount they knock things off. And so the problem is that these go the same direction. If you're on like let's say a line of constant pressure following the ideal gas law, if you're in hotter gas, it's going to be also less dense, and cooler gas is going to be denser. And so you could say, if you're just talking about photoionization, then you're going to say, oh, okay, oxygen 6 or like neon 8 or like high ions are going to live in these low density clouds. But if you're talking about collisional ionization, you'll say high ions live in hot clouds. And the thing is, you'll be talking about the same cloud because your hot clouds are also going to be low density. So we have to keep, what is the point of keeping track of both of these things separately? And well, if you don't keep track of them separately, then you'll kind of misunderstand what's going on. So here's an example. This is the oxygen 6 ion fraction plot. So this is a contour plot. It's kind of like a topographical map. So the center of these concentric circles is like the highest point, and the lowest points are down here and over here where you don't have very much oxygen 6. So this is the fraction as a function of temperature and density. And so there's two peaks on this graph. We can call them the collisional ionization peak and the photoionization peak, because one of them is temperature independent and cold. That's this one. So going up and down doesn't change much with temperature. It changes a little bit, but it changes faster with density, like this way. And the other one, which is density independent and hot. So it doesn't change at all left to right, but it changes a lot up and down. And so, we can just say, okay, that's our collisional ionization peak and our photoionization peak. But here's the thing that's weird is that here's the position of the oxygen 6 from the last graph, this is the gas that it's supposed to trace out. And you can see that this is the correct, y-axis peak, and this is the correct x-axis peak, right? This does align with these two peaks, but it's not actually at either peak, right? It's kind of far from both. So if you are looking at oxygen 6 and you are saying it's tracing out hot gas, it's going to have to be a higher density than you think, because it can't trace out hot gas that's also low density, at least not as well as it traces out either hot gas that's higher density, or it traces out kind of cool gas that's low density. So it's that makes it confusing. And what if you have a high amount of oxygen in areas with a low fraction, right? These aren't the only things that regulate the oxygen 6 amount. You also have to deal with how much oxygen is there. Like if there's a lot of oxygen up here and there's not any oxygen down here, then you're going to get mostly collisionally ionized stuff, even though, you are getting contributions from both effects. So, and this matters a lot for our simulation. And we'll talk about the simulation a little bit more in a moment, but essentially oxygen 6 is significant all throughout the space between these two peaks. So the highest amount of oxygen is in the green area. That's where we get the most mass. Oxygen 6 is in the contour plot. So like this area, this red box is kind of where we expect to see the most of it. And so we'll have to be very careful to define splitting these two peaks. So what we're going to do is we're going to take a step back and go into how cloudy actually works. So cloudy is where we got that contour plot in the first place. So what it does is it takes collisional ionization equilibrium and it populates all of the states according to the temperature, and then it will add photons. And so the way the photons are added is if you're at very high density, then the photons won't do much because your photons per atom is going to be pretty small amount. And if you're at more of a low density, then as you go from right to left in this graph, you're getting more and more photons per atom, and you'll become more and more ionized. So that's what we see here is that all of these states, these are all the oxygen states as a function of density at a constant temperature. And so we start out on the right with no photons. We have certain states. We have, oxygen 4, 5, 6, and 7 all are present. And as we go from right to left and we add photons, they all go down and decay to 0. So what we figured out was that there are only 3 possible shapes to this graph, and that'll help us define collisionally ionized or photoionized temperature snapshots. So what I mean is that the 3 kinds of shapes, and we see all 3 of them in this image, and they're highlighted in each of these things. The first shape that we can see is what we're going to call photoionized gas. So that's where we have the gas is always density dependent. And instead of stabilizing to some kind of flat shelf at high density, it just goes to 0. So if it basically has no contribution at high density at all, that means that you didn't get any of it from collisional ionization. You must get all of it from photoionization. And so at this temperature, the only ones that are photoionized are oxygen 8 and 9. On the other hand, you can have a collisionally ionized gas or ion, and that is where you start out at a high shelf, and then as you increase the amount of photons, so going from right to left, you're increasing your photons, you don't actually gain this atom. You don't gain more oxygen 4 and 5 in this picture. When you go from right to left, it just stays flat until you start to lose atoms. So that means that all the oxygen 4 and 5 you have at this temperature is basically from collisional ionization. So it starts at collisional ionization, and then when you go from right to left, you don't get any more. So you don't gain anything from photoionization, even though photoionization destroys that state. And the third picture that you could have is kind of a combination of the two, where you have some appreciable like flat shelf over here, but then it actually increases as you go from right to left. So first you start out with some collisionally ionized gas, and then as you go from right to left, you increase your amount that's getting photoionized gas, and eventually there will be more photoionized than collisional. So on the left-hand side of the factor of 2 above this shelf is, on the left-hand side of it is photoionized, on the right-hand side is mostly collisionally ionized. Okay, so with this definition, what we were able to get is a graph that looks like this. So essentially, instead of using the idea of photoionization equilibrium or collisional ionization equilibrium, we have the different mechanisms contribute to the different ions in different places. So for example, if I had gas that's in a state like this, right here, and I could see, let's say, oxygen 6 and 7, and I could see oxygen 8 and 9, those wouldn't be created through the same mechanism. At this point, oxygen 8 and 9 are still created through photoionization because it's not quite hot enough to actually get you an appreciable amount of those ions. And the other states would all be created through collisional ionization because it's basically too hot for them to be, they'll be seeded according to their temperature, and then adding photons will just bump them up to this state. And if you're down here, the opposite is true. Like if you're at this point, you'll see, only oxygen 2 and 3 are created through collisional ionization, and most of the other ions are created through photoionization. So just to show this isn't crazy, this is where this goes on the actual oxygen 6 fraction plot. So as we expected and as we kind of hoped, this splits up the two peaks just like we wanted. But now we understand what to do in this region in kind of the border of these, which is that it's basically a temperature cutoff at about 10 to the 5.3 Kelvin. So that we're going to use this to define the difference between photoionized oxygen 6, which is cold down here, and collisionally ionized oxygen 6, which is hot up here. But this applies to basically any ion. We're just going to analyze oxygen 6 primarily in this talk. Okay, so what we're going to do is we're going to apply this distinction that we just made to a simulation called VILA. So I showed the phase plot of VILA earlier as kind of a preview, but let's talk some details about the simulation. We're going to try and figure out, which of these two mechanisms is more important for oxygen 6 in simulations first, and then we're going to talk about what it might mean for interpreting observations. So we're using what's called the VILA simulations. This is 35 high-resolution zoom-in simulations, which create realistic galaxies. So there are a few things that we should say about them. So they have pretty good realistic cosmological boundary conditions. Then they run from like really high redshift, so it runs through, all of cosmology, and from very high redshift to very low redshift. And it gets pretty good resolution inside the galaxy. So it goes down to about 17 parsecs inside the galaxy. And this means that it has pretty good, because it's adaptive, it can't get worse too quickly. It has pretty good resolution in the halo. So it's a zoom-in simulation. It's not going to be perfect resolution, and it's not going to be the same everywhere because that would be too computationally expensive, but it gets decently good resolution in the halo, about 1 kiloparsec. And that's what's being showed here is the mass fraction in cells of a certain size. So the solid line is all of the VILA simulations that we analyzed. And we see that within 0.1 to 0.3 RVR, it's within most of the mass is in cells of about either a few hundred parsecs up to about 1 kiloparsec, and between 0.3 and 0.6 RVR, it's up to about 2 kiloparsecs, and between 0.6 and 1 RVR, it's still about 2 kiloparsecs. So, our mass is mostly in these relatively good resolution cells, even if there are a few low resolution cells out there. And our VILA 7, which is going to be our example galaxy that we're going to show several pictures of, is even slightly better than that. So that's these dashed lines here. A couple things to mention about, the VILA galaxies. We don't include AGN here, and that might be important. So we're definitely going to come back to this question and try and answer, if any of our conclusions change when we add AGN to a simulation like this, but for now, it's worth keeping in mind. And our simulations only run down to redshift 1 for kind of computational reasons. So that means that it's somewhat difficult to compare directly with observations, but we'll still do what we can with it. So here's what the picture of the galaxy looks like. This is Vela 7 at redshift 1. And what's going on, this is a very, very zoomed out image. This is up to 6 virial radius. So this is kind of outside the zoom in region. We wouldn't want to use too much gas out here, but there's not much here, so it doesn't really have too much of an impact. So it flows in from the sides and the bottom. So we have this cool inflowing streams that are feeding this galaxy here. And the CGM of this galaxy is this green circle, which we're going to say is our vir. So Vela 7, its basic properties, it is about 10 to the 12 solar masses in virial mass and about 10 to the 11 solar masses in stellar mass, so about 10%. And we see these 2 streams that look like they merge into one that's wrapping around clockwise from the bottom right. So we're going to see this stream basically in each of these pictures. So I want to point it out here. Okay. So before we talk about oxygen 6, let's just look at the big picture of the CGM. So we're switching from a projection plot, which we were using in the last image, to just a single slice. So this slice is basically infinitesimally thin, and it is just showing you the density, temperature, metallicity, and pressure within the virial radius. So now this black circle on the outside is our vir, and the smaller black circle is 0.1 our vir, which we're going to say is the galaxy. So everything outside of the small circle and inside the big circle is like our CGM. So what do we have to say about this? This basically shows that same inflowing filament. So we said before it was wrapping around clockwise like this from the bottom right. And since this is an infinitesimal slice, the clouds can basically go in and out of frames. That's why this looks kind of broken up. But it is the same object, just kind of, maybe oscillating in and out of the frame here. So we see that there are these inflowing streams, which are high density, low temperature, and low metallicity. Although the metallicity is not staying completely low, it's actually increasing as you go towards the center. And we'll have some interesting things to say about that in a little bit. And the outflowing bulk material is, low density and high temperature. You can see that it's outflowing when we add the velocity arrows here. So it's going pretty fast at about 1,000 kilometers per second. And the thing that I want to bring your attention, the other thing to point out here is that neither of these things show up in the pressure graph. Pressure is actually not super indicative of these inflowing streams. They're not at low or high pressure really, compared to the outflowing bulk. It's basically pressure is just depends on distance, and it doesn't seem to depend on which of these states you're in. So this high density times this low temperature equals about the same as this low density times this high temperature. So well, this whole paper was a follow-up to a previous paper by Santi, actually, who of course asked me to talk here. So I'm going to summarize what we've learned from that paper first, and then we're going to analyze a little bit deeper what happened with oxygen 6 when we looked at it again. So in that paper, we still used a similar definition of collisional and photoionized gas and analyzed which one dominated oxygen 6 by mass throughout the simulation. So our definition was slightly different. This line is slightly different than the one we're using now, but it basically is the same idea. It is flat in 2 places, and it has a little bit of a diagonal curve connecting the two because these 2 lines don't quite line up. And so what we learned from that was that oxygen 6 is all collisional at high redshift, and that fraction goes down with time. So what this picture here. At very high redshifts, we didn't have any photoionizing background radiation, so photoionization can't quite exist. And so all of our oxygen 6 at that point was created through collisional ionization. And then as time went on, we start to get this ionizing background radiation. Our photoionized fraction starts to increase. And then as we go to low times, we can have either the photoionization becomes dominant. So for low mass galaxies, we found that by redshift 0, basically all of the oxygen 6 was created through photoionization. And for higher mass galaxies, the galaxies start to increase their amount of photoionization, but then as they get really hot, they start to increase their collisional ionization again. So the oxygen 6 starts out all collisional, goes down, becomes mostly photoionized, and then starts to come back up, depending on the mass of the galaxy. The other thing we found was that oxygen 6 is more photoionized the further you go from the galaxy in each case. So the collisional ionization fraction is always higher on the center than it is on the outer edge. So this is the at 2 different redshifts. This is at redshift 3.5, redshift 1.5, and redshift 0. So this is analyzing the same galaxy as we analyzed on the top, the Vela galaxy, and analyzing another set of galaxies that we're not going to talk about today, the Nihao galaxies. So, but what we didn't know at the time is we didn't look at sightlines as much. We weren't sure how this translated into looking through, actual like line of sight, which was how you would compare to an observation, because we needed to talk about absorption spectra. This gave us some valuable insights into like trends, but we still wanted to track photo and collisionally ionized gas as separate populations. So that's what we were going to do here. We're going to apply the definitions of PI and CI gas that we made earlier as a binary field. So now we're looking at oxygen 6 density within that same slice. So this is the same slice we were looking at last time, but split up into 2 parts. So basically what we can do is we can just ask our simulation analysis software YT to multiply a cell by 1 if it's photoionized and by 0 if it's collisional. That'll give you this graph. Do the opposite to give you this graph, and then you can separate these out. So what do we see here? What we see is that the cool streams that we were talking about before are made of photoionized gas, and the hot bulk region is made of collisionally ionized gas. And this isn't really a surprise. Of course, we already knew that photoionization versus collisional ionization was basically just a temperature cutoff. And so if we want to know which one of these is more important, is we basically have to analyze, okay, this is a small amount of space, but very high density in oxygen 6, or relatively high density in oxygen 6. And this is a larger amount of space, but low density. So which one should win, right? Which one of these should be more important will depend on how much higher the density is and how much smaller these clouds are. So we're going to do some quick math here. Usually people's intuition is that cold streams are metal poor, and therefore when you see metals, it's not in these cold streams. But metallicity is only one of 4 variables here, and it's actually not the most important one for seeing a specific ion. So in fact, what we make a certain mass of an ion out of is you need 4 variables. So you have your constant amount of, like, let's say oxygen abundance. That's not going to change no matter where you are in the galaxy, more or less. I mean, you can have slightly different sources of oxygen, but they mostly all come from supernovas. So you have a constant abundance of oxygen times the density of your gas, times the metallicity of your gas, times the volume of your gas, and then times the fraction that is in your ion state. So those are all shown here. Basically, if we want to know which one of these is more important, first let's leave out oxygen fraction, or oxygen 6 fraction, for a second. This is 4 orders of magnitude difference between the stream and the bulk. In density, it's about 3 orders of magnitude difference in metallicity. So the stream is higher density, lower metallicity, and the volume is about 1/10. So about 1/10 of the volume is in these inflowing streams, and about 9/10 is in this outflowing bulk. So our total amount is 4 minus 3 minus 1. So our amount of total oxygen inside the streams is about the same as oxygen outside the streams. So it all comes down to ion fraction. And in that case, it's not close. The ion fraction is much, much higher on the inside of the streams than it is on the outside. So now our question is no longer like which one should win, but we have kind of a different question to ask, which is, why isn't photoionization dominant? Right? It looks like the photoionized stream should dominate in oxygen 6 because the fraction has a huge contrast, about 8 orders of magnitude, rather than these 4, 3, or 1. And it's pretty localized inside the streams. So why don't we get that dominates more, right? Why do we see collisionally ionized gas at all? And so to answer that question, we're going to look a little bit closer at the collisionally ionized gas. So this is the same image we showed earlier. Collisionally ionized gas has basically really low kind of red, orange oxygen 6 density, except if we zoom in. And on the very edges of these photoionized clouds, we found that the collisionally ionized gas is actually comparable to the photoionized gas, right? It's more kind of blue-green. And, it's in a very small region, but, does this matter? Does this change the conclusion that we just saw in the last slide? How much of this collisionally ionized gas is in this interface? And the answer is almost all of it. So the question of photoionization versus collisional ionization is actually not so much the streams versus the bulk material, but it's the streams versus these tiny interface layers. So the way we were able to analyze this was we tagged each interface cell by saying, if you are a collisionally ionized cell, but you're within a certain distance, here 2 kiloparsecs of a photoionized cell, then you're the outside of a photoionized cloud. And when you look at those cells in particular, you see that about 90% of the oxygen 6 that was collisionally ionized is inside this tiny interface layer. So in all 6 galaxies, we got that oxygen 6 is about 2/3 photoionized by mass and about 10% photoionized by volume. So that's the inside of the clouds, 90% collisionally ionized by volume. But the vast majority of the collisionally ionized oxygen 6 is within this interface layer. So what we've done is basically our definition of collisional and photoionization helped us find that there were these interfaces on the photoionized clouds that otherwise we wouldn't be able to tell were different than the original clouds themselves. And there's still actually a bit of a question to be asked about whether these are real, whether this is a real state or whether this is just the fact that we applied a cutoff doesn't mean that this is physically meaningful, but we're going to analyze that in a little bit later. First, we're just going to take this for what it is and say, okay, this tells us how we get our collisional and photoionization effects. So here's what the distribution actually looks like when you look at sight lines. So this is an integrated picture. So each pixel of this image is a sight line that's going kind of into the page, right? So going this way. And so we have 3 different things that can happen here. So if a pixel is all blue, then that means that all the oxygen 6 you ran into was photoionized. And if a pixel is all red, that means that all of the oxygen 6 you run into is collisionally ionized. And if a pixel is white, it means it was about 50-50. If a pixel is black, it means you've got a non-detection. So basically, we went in and just artificially said, if you're not going to see more than 10 to the 13 atoms per centimeter squared, you're basically not going to be able to detect it. It's not going to be comparable to observations at all. So what we found is that individual sight lines are all photoionized outside about 0.2 to 0.3 ARPure. So what that means is that since we talked about, we have these, the collisionally ionized gas comes from these interface layers on this photoionized inflowing clouds, then what's going on is as you get in further, the interface layers become more important than the clouds. And on the outside, the interface layers are less important than the clouds. And that's why we see the effect that we saw in Roca-Fabrica 2019, which is that the inner part of the CGM is more collisionally ionized. So yeah, there's a couple things to say about these. We have pretty high covering fractions out to RVIR, but what we see is we only see oxygen 6 when we go through those inflowing streams. Right, this is the same streams we've seen before, this flowing in from the right and curling around like this clockwise rotation. If we miss the streams, then we get nothing. And if we go through, and if we don't hit a stream, we get a non-detection, so that's black. So this is a different picture than what we saw before because the colors are changing, but ignoring the colors, basically that's what we're looking at. Here's a kind of a more quantitative view of that same thing. So in this case, the median sightline oxygen 6 column density is a function of impact parameter. So what we're showing here is the amount of oxygen 6 that you see as a function of how far away the sightline is. And what we see is that on the inner part of the CGM, the sightlines go through are collisionally ionized mostly. So the red line, the green line is the sum of the blue and the red. And on the inner part, the red line is where most of the green line comes from. On the outer part, it almost all comes from the blue line. So the collisionally ionized gas kind of drops off really rapidly as you go out, and the photoionized gas stays pretty constant. And so I put on here the COS halos observations of oxygen 6. And for a couple reasons. One is I wanted to note that we do kind of underpredict the value here, right? This is a little bit lower. It's about half an order of magnitude lower than we want. That may have something to do with that we're at redshift 1 and COS-HALO's observations were at redshift 0.3 or so. But the bigger point of the COS data here is that most of these detections are outside this transition. Most of the detections are out here after about 0.2 RVR. And, so those are most likely detections of photoionized oxygen 6. And on the inner part, we had a few detections from COS-HALOs, and those are most likely collisionally ionized oxygen 6. And so, we might want to be careful if we try to fit all of the oxygen 6 data in one bin, because the inner part and the outer part might be coming from different phases. The biggest takeaway is that both of these mechanisms matter in the CGM, and it's very hard to just choose one and assume that that's going to, be in equilibrium throughout the whole CGM. So you should still be a little bit skeptical of these interface layer story, though, because what we call an interface layer might just be the result of applying this arbitrary temperature cutoff to our streams, right? We said above 10 to the 5.3 is one thing, below 10 to the 5.3 is another thing. And, that's like saying we're looking at this object and we've put a water line in here, and then we're saying, okay, this thing is clearly one object, this is clearly another object, but we drew the line ourselves. So are we sure that that's a real effect? Because especially since, if you have high density and low temperature regions and low density, high temperature regions, and it varies continuously, then fundamental theorem of calculus says that you will eventually get to a medium temperature, medium density region. So is it really distinct enough to be treated separately? Like, should we think of the interface layers and the clouds as two separate things, or should they be just considered the clouds and they increase in density as you go to the edge? And if so, what causes it to happen? So let's stop talking about oxygen 6 for a second and look at some other ions in the CGM without these cutoffs. So this is carbon 4 and neon 8. Like oxygen 6, they're all lithium-like, which makes them easier to observe. Have 3 electrons, but they are otherwise not that similar. Carbon 4 has a much lower ionization energy. Neon 8 has a higher one. But I put them in a slide because they show something interesting. So I'm going to zoom in on the biggest cloud here. That's this like inverted Y shape on the left-hand side of the screen, or of the previous image. And the interfaces actually show up in these images, even though we haven't applied any cutoffs whatsoever. So for neon 8, it's actually really striking because the interface is a stronger neon 8 density than either the inside, where it's too cold for neon 8, or the outside, where it's too low density for neon 8. And carbon 4 kind of has a similar effect. Of course, carbon 4 likes to be inside the streams and does not like to be on the outside, but you can see this yellow line is a pretty consistent size, pretty consistent thickness, and is basically aligned with where we saw collisionally ionized oxygen 6 before. So these interface layers do show up in other ions, even when you don't apply any like special cutoffs. There is a coincidence here, but the coincidence is just that oxygen 6's cutoff between photo and collisional ionization happens to be the same as the temperature difference between the streams and the interfaces. So that might not happen for in the real universe. If the phases of these inflowing streams and the outflowing bulk are slightly different, then oxygen 6 might not even be the ion to detect this difference, right? Because it was only a coincidence that the oxygen 6 cutoff found the interface layer, but something has to find the interface layer, right? There is a significant difference between the interfaces and the streams, and so we have to just basically look to see which ion is most likely to detect that and how we're gonna find it. So let's talk about the interface a little bit. So first we thought this might be a shock condition, but it turns out that can't really work because it's not high pressure. We saw a pressure graph earlier and it didn't outline this interface layer like this. Some stuff in the literature says this might be a conductive interface that kind of protects clouds through magnetic fields, but that's not what's happening for us because we don't have any magnetic fields in the simulation. And then we talked with a collaborator who actually gave a talk at this seminar a couple of weeks ago about this, near Mandelker, whether this might be a Kelvin-Helmholtz instability layer. And that actually looked pretty plausible because we had Near had made some other papers predicting what effects that might have and how that would help streams survive in the hot CGM. So, sorry. So let's talk about Kelvin-Helmholtz instability just a bit. Basically what that is when hotter, lower density gas is moving past cool clouds in pressure equilibrium, you have turbulence forms at their edge. This is a picture from Fielding 2020. So you have hot gas moving to the right and cold gas moving to the left here. Actually, I think it's the other way. I think the cold gas is moving to the right, hot gas is moving to the left. And when that happens, it will basically create this kind of fractal interface structure. So it'll create this interface layer between these two things. And the thing that Near found was that if Kelvin-Helmholtz instability cools faster than it disrupts the stream, then instead of damaging the stream, instead of the hot gas disrupting these cooled streams, it'll entrain more gas into the cool phase, right? As they're cooling faster than they are basically crossing the stream. And so if that happens, you can get a certain amount of mass that is basically conserved or increasing as it goes into the center, rather than kind of dissipating or becoming disrupted. If you're at pressure equilibrium, i.e. your interface, so this allows you, actually I should say, to have your streams and your interfaces and your bulk all in pressure equilibrium with each other. So that would just give you a density of the interface that is the average, the geometric mean of the bulk and the stream density. Same with temperature. So rho times T is the same everywhere. And that's what we saw. That's good. And we estimate, now that we know that the mass is basically conserved and we know the density, we can estimate the volume of the streams. So one thing that we can use to check if our things follow Kelvin-Helmholtz instability regulation is whether the volume of them is what we expect. So we expect the radial size of the stream should be a power law related to the density of the hot phase. And the math on this was worked out by Near in Mandelker 2020. But basically, if we have a density that's going as r to the minus beta, so you're getting lower density as you go further out, your size of your stream should be increasing as beta over 2. So we'll test how that works. And the thickness should be about 2 kiloparsecs. So that's not super well resolved in our simulation, right? That's only a couple cells across. But the good news from Fielding 2020 is that the structure is actually, well, maybe it's good news. The structure is actually a fractal. It's much more complicated and is probably unresolvable with almost any simulation, even those like very high resolution, like foggy simulations or whatever. So this couldn't really ever be resolved in a simulation, but it can be accounted for in other ways. And those accounting for it shouldn't affect its bulk, temperature, and density. So its oxygen 6 fraction should be okay. With the caveat that it might not be in ionization equilibrium anymore. So the way cloudy works is it assumes that you're in ionization equilibrium because you've waited long enough for all of your oxygen, if it's going to be ionized out of oxygen 6 and back into it, recombine back into it, let that stabilize. If the gas is only in this interface layer for a short time, because it's going to cool and join the stream, then maybe it won't actually reach ionization equilibrium in time. And so I have a slide that I can show about what happens when you're not in ionization equilibrium, but ultimately we have to go with this because we don't have any way to generate this on the fly without using the cloudy tables. So let's check. Does our 3 phases actually follow the rules that we expect to be a Kelvin-Helmholtz instability layer? So for density, so here's our density and temperature. In density, it seems like totally. The interface layer is almost exactly the geometric mean of the density of the streams, which is high, and the density of the bulk, which is low. In temperature, it's a little bit different. So in Mandelker 2020, they found, or they assumed that these 3 phases were temperature, like constant temperature throughout space. We find that that's not quite true. These are, this one, the cold streams get a little colder as you go in. The hot bulk gets a little hotter as you go in. And the interface doesn't quite follow the geometric mean of the 2, but actually stays a little bit more on the hotter side. But these are moving pretty slowly. These are fairly flat compared to these densities. And so we're going to say that it works out okay. Especially since the more compelling thing maybe is that the total size of the stream, which, as we said, we know because the mass is conserved and the density is known of the stream, that the size of the stream should be r to the beta over 2. So scale as the negative half of the the power law for the bulk, sorry. So it's hard to identify a single stream, but what we can do is if we integrate all the streams together, then our total volume inside the streams should be this number squared, so beta over 2 to beta, and then plus 1 because we're integrating. And that's actually almost exactly true. So when we look at the power laws here, the density of the bulk is about negative 1.47, and the slope of the volume by the end is about 2.4. So right, the negative of that plus 1. So this seems like the Kelvin-Helmholtz instability layer is a plausible reason for why our streams stay the size that they are. And it regulates the size of the streams as they go in. And so what are we going to do with this? So in the last couple of minutes, I'm going to talk about our possible model for how we're going to use this, which is we have 3 phases. We have this low density outflowing gas, which is orange here. We have this high density inflowing gas, which is blue, and it has a certain characteristic size of the stream A with a certain sized interface layer delta. And so what we're going to do with this is say that most ions, except can be regulated by this shape. So as you go further in, the densities change and the fractions change, but the shape of these inflowing streams basically stays the same. So the hardest thing to deal with is these ion fractions, because usually what people assume is that the ion fraction is constant within a certain cloud, right? You have a cloud of a certain size and a certain density and temperature, and therefore it has a certain ion fraction. And then when you look for different ions, you basically have to go into a different cloud. We're going to say there's only a few clouds, but they have differing temperatures depending on how far away you are from the galaxy. So to deal with the ion fractions, we're going to think, instead of clouds of oxygen 6, we're going to think of structures that have ion fractions of oxygen 6 that depend on density, and that increases towards the center. Since the temperature change is small, so what we're going to start with to do here is assume that temperature changes are small compared to density changes, and assume these 3 phases are fixed temperatures. So that's basically making this approximation. That's not a great approximation, as you can see here, but these are varying slowly in temperature and varying much more quickly in density, so it should work okay. And the reason this is helpful is because we know what to do at a constant temperature, right? We have constant temperature snapshots like this, then we have density as a function of temperature. Can take one of 2 shapes, right? We have a collisionally ionized shape, which is this, right? We have this flat shelf that declines as we go here, or we have, and that can be approximated as 2 power laws, flat one, declining one, or we can have photoionized gas, which can be approximated as 3 power laws. And so your ion fraction can be assumed to be kind of a power law with density, and therefore a power law with radius, as long as you're basically in a region where you don't have a break between multiple power laws. So for example, for our stream, the ion is oxygen 6. Our temperature is this is the temperature of the stream, and the densities of the stream vary from roughly in here on the inner part of the halo to out here on the outer part. And so in this region, oxygen 6 is basically just a declining fraction with increasing density. So this is just a power law, more or less. On the interface, we have a basically flat region here. So this is our characteristic temperature of the interface. Here's the densities the interface kind of goes through. And the oxygen 6 fraction stays approximately flat. It starts to go down a little bit, but it stays close and it's fairly high. About 10% of the gas is oxygen 6. And in the bulk, we have a very low fraction, and it's also not very straight. It seems to be like a broken power law here. So we expect that the ion fraction in each phase to be a power law in the streams, flat in the interface, and a broken 2-part power law in the bulk. And that's exactly what we see here. So green is the flat line. Basically, our ion fraction in the interface stays constant throughout the CGM. The ion fraction in the bulk, or in the streams, gets lower as you go towards the center. And the orange line in the bulk is a broken power law. So it is going down as you go towards the center, and then it stays basically flat after some point. Okay, so we combine that with a two other things. So we need, we have our fraction, we need density and metallicity as well, because those are parts of our graph. And so when we take our density of gas and our metallicity, which are also power laws, that's worked out by other people. I'm not the expert in why these are also power laws with radius, but if we say they are, they can combine together to give you an oxygen density, which combines with the oxygen 6 fraction to give you your oxygen 6 density. So what's the point of this? The point is that we can break up our oxygen 6 density can be written as, the sum of oxygen, which is a very nice straight power law in each of these three phases, times our oxygen 6 fraction, which in the log space means you can just add these curves, this curve to this curve, to get your oxygen 6 density. So there's two things. So this is the same graph we showed in the last slide. There's two things that I want to stress about this, that I want to bring your attention to, and this is kind of maybe where I'll stop the talk. First one is that since the interface gas is collisionally ionized, it is flat in ion fraction. So that since this is flat here, this flat green line combines with this increasing green line here to give you a collisionally ionized gas, which surpasses the photoionized gas at about 0.2 RBIR. So what explains why the oxygen 6 becomes mostly collisional as you go towards the center is not because the sizes of the streams versus the sizes of the interface, but because the interfaces are staying, because they're collisionally ionized, staying about constant with density. Sorry, they're staying about constant fraction as you go in and getting more oxygen, whereas the streams are becoming very, very low. So that's why we see this. And in general, collisional ionization is going to be easier to interpret because it's this very simple flat lines. On the other hand, looking at the blue lines here, we see something that I don't think people necessarily appreciate enough about ion fractions, which is that even though this goes down a lot, this goes down from about 10% of the oxygen is in oxygen 6 to about 1 part in 10,000. Our amount of oxygen 6 in that phase actually doesn't change very much because this is increasing by a lot of orders of magnitude as it's going in. So if you're getting a lot more oxygen on the inner part of the CGM, even though you're getting a lot lower oxygen 6 fraction, the point is that they actually still, the orders of magnitude line up. They can still balance each other. This is kind of a coincidence that this, perfectly balances this increasing and decreasing streams. But the point that they could balance each other needs to be kept into account. And you can't write off parts of your oxygen 6 clouds just because they have a low fraction. Okay. And the last thing that I want to stress here is that the orange line, even though this is a nice power law here, since this one was a broken power law, we end up with something very complicated here that goes up and down. This is like a low amount, so it kind of doesn't really matter. We're never seeing this when we look at a sight line, but just the fact that the point of this is that this can be applied to any atom. And if an atom has a power law break in its fraction, then it's going to be much harder to interpret than when it doesn't, like these two. Okay, I think in the interest of time, I'm going to skip this this last thing. Actually, let's go ahead and do it very quickly. So this model, how well does it actually compare to COS-HALO's data? So in Stern 2016, they found that there are two things in COS-HALO's that were hard to explain. First is that low ions always seem to come with high ions. So silicon-4, neon-2, magnesium-2 always came with oxygen 6. You never saw them without it. However, you saw the opposite thing happen. You could see oxygen 6 without any low ions. And that was really strange. Like, why would these agree with each other? They're supposed to be living in different clouds. And what they argued for was for a spatial connection between clouds of different densities. So they said, okay, let's say that in low density clouds, here's oxygen 6 column density as a function of hydrogen 1 column density in the COS-HALO's data. And what they found was that, okay, if you increase your hydrogen 1 density, first you increase your oxygen density with it, because if you don't get enough hydrogen, that means you're not going through a cloud dense enough to even contain oxygen 6. But then once you go through a cloud that contains oxygen 6, increasing your hydrogen density further doesn't give you more oxygen 6, because now you're going through denser, smaller clouds that are inside those previous clouds. And so we get this kind of spatial connection. We have these smaller clouds that have higher density and therefore lower ions that are contained inside these bigger clouds that have higher density, or sorry, that have lower density and therefore higher ions, like oxygen 6. So we actually fill out the same kind of structure here, but we can think of it a different way. So instead of saying that our clouds, we have clouds inside clouds of different densities, we should think about these 3 different phases as sort of separate, contributing separately. So we're going to interpret this as like this inner part where we have oxygen 6 increasing with H1 as being where you kind of don't hit one of the inflowing streams. So if you don't hit an inflowing stream, you're going to get a low amount of both oxygen 6 and H1. In this region, the green region here, you're hitting the stream and you're getting a decent amount of oxygen 6, but you are not increasing, you're not getting a lot of other ions because in that region, it's basically too hot for other ions to live. Then as you go further in here, you're not increasing your oxygen 6 fraction very much because the oxygen 6 is basically, the oxygen 6 fraction is going down as you go closer in because it's getting too cold, but you're starting to increase your other ions. So this is where you'll detect kind of low ion states. So here's where you can detect oxygen 6 without low ions. Here's where you would detect oxygen 6 with low ions. So we could check, we'll check this in future work, but for now, that's kind of the interpretation we can give to this flattening curve that was found in Stern 2016. Okay, so what we're planning on doing into the future is doing kind of more detailed comparisons with observations. So the COSMA data will allow us to do comparisons all the way up to redshift 1, which will be good. And using other ions besides oxygen 6, which we found has 2 different states that matter, the interfaces and the streams, it might be easier to interpret something if it was only one state. So we're going to look at other ions. Neon 8 seemed promising because, as we saw, it just tags the interface layer more than either the inside or the outside of the streams. So we're going to see what effect that has. And I think with that, I'm going to go ahead and skip to a conclusion slide and say thanks everybody for your time here. So conclusions, we have basically, we defined PI and CI gas. And then we said, we looked in the simulations, found that PI lives in cooled inflows, CI lives on the interfaces, which we understood to be fairly physically meaningful and could contribute a new model for how the CGM actually is constructed in all ions. So with that, I'll ask for any questions. And yeah, thanks for inviting me to give this talk.
Great. Thank you a lot, Clayton, for the description of your huge amount of work on the CGM studies. And now, as you said, if somebody in the audience has a question, please just raise your hand and you can make the question. Also, please tell us your name and institution before starting with the question. So if somebody has a question. I have some comments, but I more or less know very well the work, so I have no lot of questions today. But I see that Isabel Marquez has a question. So Isabel, as you, when you want, you can start with the question.
Okay, thank you very much. It's a very nice talk. Thank you very much, Clayton. I wasn't completely, fully attentive because I have been interrupted. And so maybe you have already said that, but just so in that case, yeah, excuse me. I'm an observational astronomer, so we are mainly using other ions, mainly oxygen-3, for instance, in the optical, or H-beta or sulfur-2 or things like that. So why did you select oxygen-6 and instead of other ions that we are much more used to analyze for galaxies from the observational point of view?
That's a good question, actually. I think I didn't mention this, but the primary reason for looking at oxygen 6 is actually a resolution question. Basically, what we think is that, and this was done by, I think, Kelvin-Helmholtz has a good paper on this, but is that in these simulations, these cosmological simulations, when we're looking out in the CGM, we have kind of worse resolution than we would have inside the galaxy. So if low ions like, magnesium 2 or like silicon 4 or whatever, like, and I don't know exactly which, but any low ions that are, less than oxygen 6, you might have them in tinier clouds that might not be fully resolved. So we think that this shouldn't have a huge impact on these higher ions, but it's once you get lower ions, you're going to have these smaller and smaller clouds, and the closer they are to your resolution limit, the more likely you are to just not see them or see them kind of wrong and not be able to use them. So that's kind of the main reason we started with oxygen 6. Also because it has a lot of debate basically about whether or not it's collisionally or photoionized. There's several papers arguing for one or the other, using either simulations or using kind of observational metrics, or assuming that it could be both. And I guess that's kind of what I've found, is that both mechanisms contribute, and that makes it kind of especially interesting. But thanks for that question. The biggest the resolution effect.
Okay, so may I have another one?
Yeah.
It's related with, I think that you've said that you don't use AGN, right? Because they may be producing very energetic photons to ionize, to effectively have such a high ionization in the center of galaxies. But you don't take that into account, right? So you don't consider any AGN.
Yeah, that's not in these simulations. And actually in general, a lot of, it's kind of very new to use local sources for ionization at all. So what we're using as our sources of ionization is that when we're out in the CGM, we're saying we're basically far enough from the galaxy that most of the ionizing radiation is coming from kind of the general background rather than specific sources nearby. I know that inside the inner CGM, that's definitely not quite true, especially when you have an AGN turned on. So an AGN turned on will affect, directly in front of it a lot of ions. But that is just harder to calculate. So it hasn't been done in this current work. But yeah, we are thinking about that, and future work will definitely involve AGNs because simulations are basically able to handle it better now. It used to be very difficult to include an AGN at all.
But they can have a strong impact in the even at large distances. So we know that we have strong radio jets and going very far away in the galaxy. So and it's coming from the AGN. So in principle, it should be interesting to know how this can affect.
Yeah, that'd be very interesting. That's something that we might need to apply kind of a specialized simulation that's like, folk getting very high resolution directly in front of the AGN if we want to actually get a sense of what it does directly, because it would be very hard to do in post-processing like what we're doing here. But I think that is an important thing to do for sure.
Thank you very much. Very interesting talk. I'll say it again. Thanks.
Okay, thank you, Isabel. Somebody else has a question, please just raise your hand and you can proceed. If not, I have a question for Isabel now, just in the same line of what you said, because you are an observer and it's not common for us, the theoretians, to have the opportunity of asking to an observer about that. Which kind of ions do you expect to get enhanced by the IGN? Because basically, I expect that this will be important for massive galaxies above the mass of the Milky Way. That, if I am not wrong, Clayton, you were analyzing mostly Milky Way-like galaxies. So the AGNs will be probably more important for higher mass systems and will probably contribute on heating up the gas. But I don't know which kind of ions are you expecting, Isabel, to observe?
If you're talking about quasars, if you're talking about quasars, so very, very strong AGN, it could be right. You're expecting to have massive hosts, not extremely massive anyway, but AGNs are hosted by any kind of galaxies, or even the Milky Way. So Seyfert galaxies are found in galaxies which are not especially massive. And those are the most common kind of AGN. Quasars are an extreme kind of AGN.
In Milky Way size, and then these AGNs will heat up the gas, and then you will see basically a collisional ionization, or what do you expect? What do you observe from
you
the
have
AGN?
A power law. You have the source, the ionization source is a power law, who is photoionizing the gas, and it's not collisionally. Yeah. but with the
Okay.
special shape. I mean,
Okay.
it's not the same one as stars.
So this is something worth studying also, this photoionization by the AGN, something I had in my mind. So Clayton is something we need to talk about that. Good.
For sure.
Thank you. Thank you, Janet.
Welcome.
Okay, perfect. So I think it's time to finish the seminar. Thank you a lot again, Clayton, for the very nice talk. This will be recorded, so everybody that wants to revise the talk can do it. And if anybody has questions further in the future, you can just send an email to Clayton or to me, and I will send it to Clayton to be answered. So thank you, everybody, for coming. Thank you, Clayton, and see you soon.